Okay, solving circuits. Current. Okay, current in a circuit flows downhill. Current flows, whoop, that was a little strange. Current flows from the positive terminal of a voltage source through the circuit to the negative terminal. That's the first thing we're going to say about current. And then here is the key. When we're talking about current, by the way, what is current measured in? Who remembers the units for current? You're right, Nate. Amps. Okay? At any junction, anytime two wires or more touch, the current in equals the current out. So what we're going to do first thing whenever we have a circuit, Lena, is we're going to figure out which way is downhill. I don't know why I'm picking on. Oh, yeah, because you came in late, so you're in my mind. We're going to figure out which way is downhill. We're going to put little arrows all over our circuit to show the direction of the current as follows. I told you that a circuit was sort of like a ski hill. In terms of our ski hill analogy, here's what it really means. If you have 10 skiers coming into a hill, at the bottom of the hill, you better have 10 skiers. If you have 2 forks in the path, 5 skiers coming this way, 6 skiers coming this way, you're going to have 11 skiers on the hill. Or if I go current in my picture here, how many skiers, how many amps do I have coming in this way? How many amps do I have coming in this way? I'm telling you, that wire has to have 3 amps. Current can't vanish. So, you ready? Example 1 says, find the unknown currents. Now, we're going to use circuit symbols. We're going to use a schematic diagram. And it's been so long, I'm going to review with you. Hey, what's this the symbol for? Battery. Which part is positive? The longer line. So if you want to, you could put a little plus there, a little minus there. Now, electrons, don't write this down, electrons travel this way because electrons always go from negative to positive. But I told you that Benjamin Franklin named negative and positive wrong. It is so much more convenient, Kiana, to deal with positive numbers that we're going to pretend that stuff goes this way, and that's what we call current. Current is which way would the positives move if they could, even though they're locked inside the nucleus because they're protons and they really can't go anywhere. Let's, Jordan, just pretend they can. So first thing I always do when I see a battery, I put a little arrow saying that's downhill. Let's go skiing. Ski with me, ski with me, ski with me, ski with me, ski. Oh, how many skiers are right here? What's the current right here? 1.75 amps. They all go down this hill, this resistor. They all go down this hill. How many skiers must be here still? 1.75. Current does not vanish. Current does not get used up. Keep going, keep going, keep going. How many amps would you measure right there? 1.75. This is the current rule. And this is because a lot of students, Nicole, think, oh, in a circuit, current gets used up. No, no. Current does not get used up in a circuit. In the same way on a ski hill, skiers don't vanish unless something goes horribly wrong. Let's do a tougher one. I'm going to make this bigger so you guys can see in the back row. I'm going to try and make this bigger so you guys can see in the back row. Oh, my computer's running slow. I should have rebooted it. Oh, well. Okay. Find the battery. See it? This way is positive. And that's downhill. So let's go skiing. Oh, how many skiers, how many amps are there in this circuit grand total? Because grand total would always be what's leaving, we call this the chairlift, what's leaving the battery. How many skiers, how many amps does this circuit contain grand total? 3. Okay? Here's a junction. How many amps went this way? 0.8. How many amps must have gone this way? Do the math in your head. Got to be 2.2. This is the current rule. You know what? Let's follow this wire. Keep going, 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 keep going. Oh, how many amps must be right here? Because they haven't been able to go anywhere else. And what direction is the current going, which way is downhill in this section right here? That way, or left or right? Left. Let's circle that. Now, how many amps are going this way? 0.8. How many amps are going this way? 2.2. They meet up. Oh, how many amps are right here now? Back to 3. Oh, what direction? In fact, in Physics 12, what I tell my students, Mateo, is if you know the total current leaving the battery, you'll walk your way through the circuit. It's going to fall apart very quickly. Example 2 says, show the direction of each current and find the unknown current. First thing I do is I find the battery. Which way is downhill from the battery? Well, up, right here. So with your pencil, put a little arrow that way. Let's keep going. Which way would the current be flowing in this little line right here, to the left or to the right? Put a little arrow here. Now, right here, there's a junction. We're going to shake hands and split up. Which way is downhill in this wire? That way, right? Which way is downhill in this wire? That way. Let's keep going along the top. Let's keep going along the top. Here's another junction. Here's another spot where the current's going to split up. Which way is downhill here? Which way is downhill here? Now we meet up again. Which way is the current going in this wire? Left. Which way is the current going in this wire? Left. Now that took a long time because I did it orally. Generally it takes you about 1 second to quickly label the currents, and I think, Lyndon, that's great bang for your buck. Worth doing. Now, did they tell me how many amps left the chairlift? How many amps left the battery? Everybody say no. Okay. Can I figure out how many amps left the battery? Well, let's go to this first junction. How many amps went this way? How many amps went this way? How many amps must have been here for that to work? 13. Right? So, now I know. 13 amps. This circuit is drawing 13 amps grand total. Now, let's go skiing. Heck, let's go this way. So, how many amps went this way? Boom. How many amps went this way? How many amps must have gone this way? How many amps are coming in here? Okay, because you were talking when I went through this yakety yak. 3 amps. There's my 5. How many amps here? Got to be 3. They meet up. How many amps right here? What's coming in? 5. 2 from the top and 3 from the left for you guys. It's all backwards because I'm facing that way, so I always got to reverse everything. 3 from, sorry, no, you guys, 3 from the right. Yeah, I didn't reverse it. So 5 amps right here. Okay. How many amps? 13. Right? 8 coming in, 5 coming in, 13 amps. Current in a circuit does not vanish. Whatever current you start out with, that's what you're going to have when you get back to the bottom of your battery. Ooh. Where's the battery? The bottom. Which way is the current flowing from that battery? To the left or to the right? So let's draw an arrow like that. Current goes this way, and I guess it goes this way, and that way. Right? That's downhill, and I know that's up the page, but use your imagination. This way. This way. I guess here it splits up that way and that way. We come back. Is that okay, Jordan? So here's my question. Is there anywhere on this circuit where they told me the total current? Is there any section of wire where I know all the skiers, all the current, all the amperage had to go through it. Tristan. Right there. It's further on, but any junction came back together. So how many amps does this circuit hold grand total altogether? So you know what? That must mean I had 5 amps leaving the battery. Now that I have that, I'm telling you, Kiana, this is going to fall apart. How many amps do I have right here? 5. Keep going, keep going. 2 went this way. 0.5 went this way. How many must have gone this way? 2.5, right? And you can use a calculator, although some of these, if you're good with decimals, you can do in your head. They meet up again. Oh, how many amps here? Okay, 7 can't be because we've already said that this circuit has a total of 5 amps. The current can't come from nowhere. Okay? And this is why it's important to draw those arrows, because if you follow it, I got 5 coming in, 2 this way, and if you think of it that way, 3 amps this way. Then they meet up again, and we're back to 5 amps. I actually kind of imagine skiers that are 5 skiers on this hill, and whenever they get to a junction, they shake hands. You guys go that way, we'll go this way, and we'll meet up down below. I kind of have that little image. Okay. By the way, that's a 2.5, not a 25. That didn't look like a very good decimal. Oh, what are these squiggly lines? The symbol for? Now this is the symbol for resistors in Word when I'm in a rush trying to do graphics without getting all fancy. You know what, though? It works. Hey, where's the battery here? On the left. Which way is uphill? Up. Do I know? Gesundheit. Do I know the total current in this circuit? Look at the picture. What? 4.5, because your eyes went, hey, wait a minute. They told me the current in this resistor, and there's nowhere else for them to go. This sounds weird. There's 4.5 skiers on the hill. How can you have half a skier? Well, someone's short. No, but 4.5 amps. Okay, so how many amps are in this circuit? 4.5. Let's fill in which way. Downhill. Downhill. To the right is downhill, and down is downhill. They meet up here. I guess to the left along the bottom part is downhill. How many amps? How many amps? How'd you get that? If 1 amp went this way, 3.5 must have gone that way. You know what? Let's keep going along this particular ski run. So 3.5 amps, oh, how many amps? Because there's no other junctions. Oh, how many amps? Still 3.5. Going that way for what it's worth. Okay. Let's fill in this middle hill here. How many amps? How many amps? Gotta be. Oh, last blank. How many amps? 4.5. Does that make sense? Okay. If you were playing around with that virtual circuit lab that you were building, and you put an ammeter in there, you would find whatever current was leaving that battery was also coming back at the bottom of that battery. You could split it up along the way, because I saw some of you build some very esoteric circuits. You could, I think Omid had the record with like 50 resistors or something like that. I remember yours. Each of those would be splitting off some of the current, but I'm telling you, it would all come back at the bottom. That's current. There's also a voltage law. The voltage law says this. If you walk around a circuit, if, Candace, you go in any path so that you end up back where you started from, any voltage gains equal voltage drops. Say, what? So I've told you guys, I've told you, Damien, that a circuit is like a ski hill. Here's what we're saying. How do you get to the top of a mountain when you're skiing? Chairlift. That's like the battery. The chairlift gives you a higher height. The battery gives you a higher voltage. How do you get back down to the bottom of the chairlift? You have to lose whatever height you gained from the chairlift. You have to go down ski runs. Those are like resistors. Any voltage that you gain, you have to lose. So we're going to say that going through a resistor, Aiden, you lose voltage. It's like going down a ski hill. Going through a chairlift, you gain voltage. That's like raising your height on a mountain. So in terms of the ski hill analogy, I said here, VL, the voltage law, that's my abbreviation, simply says that the chairlift takes you to the top of the mountain, and from there, as you ski down to the bottom along any path, the sum of the drops must equal the height of the mountain. Say what? It's easier. It's easier with numbers. I'll zoom in again. It says, find the unknown voltages and voltage drops. So the first thing I always want to know is, how high is this mountain? How many volts is the initial voltage of this circuit? What's the battery? Did they tell you? 20. Okay? Which means any skiers, any amps, any current getting off right here are at a voltage of 20 volts. That's how, I'll say that's how high they are, even though voltage isn't a height. It's an analogy, and it'll actually work to explain a lot. These are just the trails leading to the hills. You're not going to lose any height. We're going to pretend the trails are dead level. So you're still 20 volts high right here. But going through this resistor, you lose 8 volts. So how many volts are we at here? 12. Now, did I tell you this one? Did I tell you this one? But how high are you always when you get back to the bottom of the chairlift? 0. Oh, so you know what? Right there you must also be 0 volts because there's no resistor, there's no hill to go down. So here's my question. If at the top of the hill you were 12 volts, at the bottom of the hill you were 0 volts, how many volts did you lose going through this resistor? 12. There you go. That's the circuit and current rules. We're just going to practice this now for a few days, but Pierce, that's it. That's how it works. Now, actually what we're going to get in the habit of doing is, instead of labeling the wires like I did, we're only going to label the resistors because it's less writing and less confusing. But we'll do a couple more where we're labeling the wires. Here's another one. Can I fit it all in? Sure. How high is this chairlift? How high is this ski hill? Hey, what's our voltage source? Because that's all the same question. So right here, we're 10 volts. You know what? Right here, we're 10 volts high. Yep.
Will it always give you the voltage drop?
Nope. Patience. Patience. Good question, but patience. Eventually, what I'm going to say to you is, if I give you any two of resistance, power, current, and voltage, you can calculate the other ones from those equations. If you know any two, you know four. And it becomes almost like a jigsaw puzzle mathematically. I kind of like these. I treat these as little brain teasers. How high are we? How high are we right here? Have we gone down any hills? No. So at the top right here, now we're shaking hands and splitting up, but we're shaking hands and splitting up 10 volts high and 10 volts high. How do I know? We haven't gone down any hills yet. Haven't gone through any resistors yet. In physics, we haven't lost any energy yet, if you want the actual physics explanation, but I'll give you my ski hill. Okay. Let's go down the middle hill. Boom. They didn't tell me anything except if I keep... Oh, you know what? We should probably put our arrows here so we know which way we're skiing. That's a good habit to do. How high are we at the bottom of the chairlift? Always. 0. So, how high are we right here?
0.
Gotta be 0. How many volts did we lose going through this resistor?
7.
Must have. In fact, that's why some of you, that when you were playing around with the virtual circuit, you may have noticed that when you measured the voltage across the resistor, you got a negative voltage. And what that's saying is you lost voltage. We usually don't put a negative there. We just understand it's a voltage drop. How would you show a drop mathematically? Negative. But we clue in resistors, you lose voltage. Batteries, you gain voltage. Hey, what about the other two? How high? 10? How high are we right here? Oh. So we must have lost 10 volts. Yep.
How are you at 10 still?
Ah! Great question. And this is where kids want to say, wait a minute, Mr. Dueck, how can you have, it looks like you're saying there's 20 volts and from a 10 volt, no. I'm saying this mountain, this chairlift is 10 volts high. Keep going. Ski with me. Have we gone down any hills yet? Have we gone on any hills yet? Have we gone on any hills yet? So how high must we still be? 10. We go down one hill. I don't know how high it is, but did I end up at the bottom? Oh, then it must have been a 10-volt high hill. What you can kind of imagine is these are two different hills that are the same height. You guys went that way, we went that way, but we lost the same voltage. Not the same current, but same voltage. Okay? Yeah, I'm glad someone asked that. This is the difference between voltage and current. Let's try another one. What's our voltage gain? How high is this chairlift? How high is this mountain? 12. So what's going to be right? Oh, you know what? Let's label the currents. This way, that's downhill. That's downhill. That's downhill. That's downhill. That's downhill. That's downhill. Now I know which way I'm skiing. For you guys, it's clockwise. Clockwise, yeah. Okay. Talk to me. 12 volts. Everybody, all the skiers, all the current, apparently went down this hill here. How high was this hill? 8. So they lost 8 volts. How high is everybody now? Which one, Aiden? 8? No. What's the answer? Start at 12, lose 8. How high are we here?
12, 11, 10, 9, 8, 7, 6, 5, 4. I think we have 4 left.
I'm pretty sure we have. So now, right here, we're 4 volts high. We split up, but are there any hills here yet? So right here, 4 volts high. Let's ski down this middle run. Jump. Did that take me back to the bottom? So right here, I must be 0 volts high. How many volts must I have lost going through that middle resistor? Must have. Now, how high are we right here? 4 volts. Oh, how high are we right here then? 4 volts. What did we lose going through here? Must have, because this hill also got me back to the bottom. 0 volts. Must have lost 4 volts. This is kind of fun, Mr. Dueck. We're skiing. Well, as much as I can do on this budget, yes. I got to make this one a little smaller to fit it all in. By the way, is that big enough you can see okay? Kind of? Okay. I'm trying to make this as big as I can. Okay, how big is our chairlift this time? 60 volts because of a very big battery. Okay. Oh, hang on here. Got to pause the video. Okay, so what's our voltage gain? 60 volts is a big battery. Okay. How high? Oh, you know what? Let's label the current. Downhill, 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 downhill. So this first blank here, how high? We all leave the chairlift 60 volts high. This first hill is 15 volts high. We all go down it. So how high are we right here? 45. Let's go down this middle ski run. What do we lose on this ski hill? 18 volts. So how high are we now? Whatever, how would I calculate it? Yeah, 45 take away 18. 27? Let's keep skiing. Oh, how high are we right here still? Have we gone through any hills yet? So right here, we're at 27 volts. We go down this hill. Oh, what do we end up at? So how many volts must we have lost going through this resistor? Got to be. Oh, let's do the right-hand hill. How high? How high? 45. It is, if, Mateo, I heard him say, this is pretty, it is if you think about it the right way. If you do not, in fact, the first couple of years that I taught this, I actually taught this all mathematically, and it was tough. I have Mr. Kreitch, who's a physics teacher over at SRT, passed on this ski hill analogy to me, and I just, oh, that is so much better than the way I was teaching it. So I have to thank him. Hey, Mateo, how many volts did we lose going through here? So what are we here now? Oh, look at that. Now, you ready? What goes there? Let's see. I don't know. What? Aiden, what? Because how high am I right here? And did I go through any ski hills? Then I must have ended up 27. Ah, is that what you were going to ask me earlier when I cut you off, Rihanna? It has to be an 8-volt resistor. You must have lost 8 volts going through there. 7? I think it's 8. 35 take away 27 is 8. You can do the counting thing. Yeah, nice recovery. Oh, 27. Oh, okay, yeah, nice recovery. I wrote here, look, although it's helpful at first to label the voltages everywhere, it gets really cluttered. So what we're going to do from now on, Kiana, we're going to label only the gains, the battery, and the drops, the resistors, but we're not going to label the wires in between. Okay? Well, I can make it a little bigger. So this is more what you're going to see in a couple of weeks on your test. It says this: find the unknown voltage drops, currents, and what? Resistance. Hey, wait a minute. Here they're giving me V and I, but they also want R. Is there an equation that has V and I and R in it? Hey, let's write over here, V equals I times R, I equals V over I, and I equals V over R, Mr. Dueck. Whoops. And R equals V over I. And what I'm going to say from now on, if I give you any two, you can find the third. Okay? So, you guys have that. I'm going to go back so I can see the whole circuit. And again, Candace, I just stole that from the yellow sheet, but instead of having to refer to a yellow sheet, it's kind of handy to have it there. Okay. Let's finally, for the first time, solve a circuit. Which way is downhill? Right? The electrons flow in the opposite. By the way, are you cluing in why it's so much more convenient to pretend that the positives are moving? Because to try to do this with negative numbers, so Benjamin Franklin got it wrong. Electrons move this way, current moves this way. We just define it that way. Okay. First thing I always look for, have they told me the total current anywhere? Do I know the total number of skiers in amps on this hill? What I'm really looking for is there any wire anywhere that I know everything has to go through, and they told me the current there. I always start out here. Do I know how many amps are leaving the chairlift? Amps? How many amps? How many amps are leaving the someone said it? 4. That's how many amps. I always start with current. That's how many amps are leaving the chairlift. That's important. In fact, I might even say, make a little note, right here is 4 amps. I knew I'd put a spot there to. Let's do the current first. So how many amps does this ski hill have grand total? 4. They split up right there. How many amps went down?
3.
How many amps went right?
1.
Have we filled in all the current stuff? Let's do the volt. I think so. Are there any other blank? Okay, let's do the V's, the voltages. How many volts high is this hill? How big is the battery? 18. How many volts do we lose going down this hill? 6. So what? How high are we? Just in our head? 12. Okay. Let's go down this way. Don't know how high? Did I get to the bottom? How high must this hill have been then? Must have lost 12 volts. Let's go skiing. 18, lose 6. How high were we here? How high must this hill have been? 12 volts. And again, I know if you add everything, all the voltages up, it adds to more than 18. Voltage doesn't work that way. Voltage is a change in energy state, if you really want to be fussy. Current is the one that works that way. Now, ready? Do I know two things in this resistor? Then I know three. How big is this resistor in ohms? You know the voltage, you know the current. How big is that resistor in ohms? Someone do the math, please. On your calculator. It's a decimal. You guys see what I'm getting at here? You know the voltage, 6. You know the current, amps. What's resistance? R equals V over A. 6 divided by 4. This is a 1.5 ohm resistor. How big is this resistance? How big is this resistor? People, you got to do this. Get your calculators out or do it in your head. Am I losing you here? Right? We're going like this. Resistance is going to be the voltage divided by the current. So what's the voltage in this middle resistor? 12. What's the current? 3. This must be a 4 ohm resistor. Otherwise this circuit couldn't work. It's a 4 ohm light bulb. What about the resistance of this right-hand resistor? Fareem, you're right. 12. 12 divided by what? 12 ohms. And again, what I'm saying here, Taya, if you know any two, you always know the third one. You can find, in fact, in a few, I'm not going to give you the currents, but I'll give you the resistor and the voltage. I gave you the current in disguise. Or I'll give you the current and the resistance. I gave you the voltage in disguise. It's all there. Let's try another one. Turn the page. Is that what it is? Sure. So we're going to find every missing voltage in each resistor, every missing current, and every resistance. Oh, hang on. Turn back one page, please. To this one. Suppose each of these resistors were light bulbs. How many watts are each of these bulbs? Have I got an equation that has power and voltage and current in it? Have I got an equation that has power? Because power is measured in what? Watts. Do I have a power? What's the power equation? Yeah, Kev.
Power equals V times I.
So you know what? This is a 24 watt bulb, 6 times 4. This is a 36 watt bulb, 12 times 3. How many watts is this light bulb? Am I losing you here? What's the voltage here? What's the current here? How do I calculate power? It's going to be 12 times 1. Yeah! It's a 12 watt bulb. So now, right? That's how the 36 watts, 12 times 3, 36 watt bulb. So now, I lied. I said if you know any two, you know 3. Actually, if you know any two, you know 4. If you know any two of power, resistance, current, or voltage, you know all of them. Now let's do the next one. Turn the page. What we're going to now do is we're going to find current, voltage, resistance, and just for the heck of it, we'll pretend they're all light bulbs. We'll find out how many watt bulbs they are, how big they are. Power. That's so much work. Yeah, because I did that all in my head. Jeez. They're puzzles. So let's start. Which way is downhill? From the battery. So let's label that current. Boom, 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 boom. I always start out by asking, can I figure out how many amps are in this circuit? And I can. This one's a bit trickier. How many amps are leaving the chairlift? How many amps are right there? Let's see. How many amps went this way? How many amps went this way? Did all the skiers have to go down this hill? Right here? Is there any other path that they can take? So, total current is... Do you see how we backtrack that? Look, There's one junction and 1.5 go one way and one go the other way. 2.5 must have been coming in, and I walked backwards. There was no other junctions between it and the battery. So, how many amps? How many amps? Also 2.5. Stop. Do I know two things? I know four things. What's the resistor here? Now, this one is probably going to be a bit trickier to calculate, but remember, resistance is V over I. You're going to need a calculator. It's 21 divided by 2.5, whatever the heck that is. Somebody crunch that for me, please. 8.4 ohms? Oh, and how many watts is this bulb? Now, remember, power is V times I, so it's going to be 21 times 2.5. I think I can do that in my head. It's going to be 42 plus 11.5, 53.5? 52.5 watts. I'm telling you, if you know two things, you know four things. Let's keep skiing. How many amps went this way? 1 amp. Okay. How high is this hill? How high did we start? What did we lose going down this hill? 21, leaving. 14. Can I get to the bottom? Aiden, what'd you say? Gotta be. Hey, Aiden, do I know two things? And I know four things. What's the resistance of this resistor in ohms? This one I think you can do in your head because it's V divided by I. It's 14 divided by 1. And how many watts of power is that light bulb? I think this one you can also do in your head because it's V times I. It's 14 times 1. That's a 14 watt bulb. Let's do the other hill. How high are we right here coming in? Let's see. How high? 35 volts. What did we lose? 21. How high were we here? 14. How many volts high must this hill be? Also 14. Is that a hand up or a stretch? Stretch? Okay. Lena, you going to make it? Yeah? You sure sat up in a hurry when I said your name. You sure? Can you guys see? This has got to be 4. In fact, you know what? There's another way to think about this. Were we able to shake hands, split up, and then meet up down here? Well, then if you went this way and you went down a hill that was 14 volts high, the only way that I can meet up with you is if I go down a hill that's 14 volts high. Otherwise, how could I meet up with you at the same height? Is that okay, Jordan? You sure you're with me? Because you look like you were zoned. Different number of skiers, absolutely. Same height hill, though. Oh, and Aiden, do I now know two things on that final resistor? Well, then, how many ohms is it? Whatever 14 divided by 1.5 is. 9.3333. I'll go 9.33. Close enough. And how many watts? 14 times 1.5, which I think is 21, but double check me. Yeah. Getting the hang of this a little bit, sort of. Strange, but good. A couple more and we're going to pause. Downhill is this way. I guess down in the middle, right on the top, left on the bottom. That's all downhill. First thing I always look for is, did they tell me the number of skiers, how many amps leaving the battery? Did they tell me the total current? Let's see. Did they tell me current? So when you're saying voltage, that's not what I'm looking for yet. Do I know how many amps right here yet? Did they tell me that? No. Did they tell me how many amps here? Because that would be total current. Did they tell me how many amps down here? Because that would be total current. They told me 1 amp here. Now, that does not mean that there's only 1 amp, because some skiers could have gone this way. But I always look for that first. Okay, that didn't help. Now, I go skiing. You ready? How high? How high? Don't know. How high? 35 volts? I ended up at the bottom. Okay, if this resistor loses 35 volts, if this hill is 35 volts high, and I start 40 volts high, how high? You must have lost 5 volts. Otherwise, how could you end up losing a total of 40? You okay with that, Casual? Let's go back to the beginning. How high? Casual, how high? 40 volts. What did we lose? How high are we right here now then? 35, right? Start 40, lose 5. We're 35 volts high, 35 volts high, 35 volts high, 35. Don't know? Got to the, oh, if I got to the bottom and I started 35 volts high, how many volts in that resistor? Must be a 35 volt drop. Again, I said to you, the other way you could think about this, you could, Leah, say, we shook hands right here, split up. You went this way, I went that way, but if you went down one hill, 35 volts, and I was able to meet up with you at the bottom, my hill must have been 35 volts high. Otherwise, how the heck could we end up meeting at the bottom of the trail? If mine was higher, I'd be further down. If mine was not as high, I'd be up high sometimes. Is that okay? Are you ready? Is there anywhere now where I know two things? Is there any resistor where I know two things? Lena nodded. She's right. Did you nod? Say you did. Yeah, there you go. That was. Well, if I know two, I know 3 or 4. So you ready? How many amps right here?
1,
How many volts right here?
35,
How many ohms?
35 divided by 1.
35 divided by 1, which every one of you can do in your head. This is a 35 ohm resistor. How many watts? V times I, 35 times 1, also 35 watts. Do I know two things in this resistor? No, come back to it. Do I know two things? I know two things here. So that must mean I can figure out the current. Okay. What's the equation that has the I by itself and has a V and an R in it? What's the equation from your yellow sheet that has the I by itself and has the V and the R in it? Aiden, what's the voltage in this mystery resistor? Look up. What's the voltage in this mystery resistor? What's the what's the resistance? 35 divided by 5. In your head? So how many amps went down this hill? How many amps went down this hill? 7. How many amps went down this hill? How many amps right there then? 8. How many amps right here? 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 Hey, do I know two things in that top resistor then? Then I know 4. What's the resistance? 8. I think 5 divided by 8, isn't it? It's V over R, is it not? 5 divided by 8, 0.625 ohms. Oh, and I didn't do the power for either of these. I said if you know 2, you know 4. So let's do the power here, and let's do the power here. Power is measured in watts. Power is V times, I can do this one in my head. 5 times 8. How many watts is this bulb? 40. And over here on the right-hand side, 35 times 7. I can't hear you. So 245, is that what you said? So here would be a neat question as a part B. Hey, which is the brightest bulb here? My mom says I'm not the brightest bulb. No, Aiden, that means something different. Which is the brightest bulb here? One on the right? Why? It's the biggest wattage. Yeah. Now, if I asked you that initially, that would be a terrifying question. If I gave you this circuit with just what I gave, without all the stuff filled in, just with the numbers that I gave you, and I said, hey, which bulb is brightest? That would terrify you. But can you see, actually, it pops out. Brightest bulb? Second brightest bulb is the 40-watt bulb, and a little bit dimmer would be the 35-watt bulb. In fact, you might not be able to tell the difference with your eyes, because a 35-watt bulb and a 40-watt bulb are pretty close. But certainly, this one here would be very bright. In fact, it'd probably be giving off a lot of heat even. It would be like one of those really, really bright floodlight kind of bulbs. Okay? We can get a lot of information from here. That's your calculator, right, Jordan? Right. How many more am I going to do here? I think what I'm going to do is... because I want to pick this up after spring break, because a 2-week gap you'll have forgotten all this. But are you getting the kind of the hang of this okay, Brendan? This is Kirchhoff's rules for circuits. The first one says current in equals current out. Current doesn't vanish. The second one says if you walk a complete circle, you better end up at the same height, same voltage that you started from, as long as we pretend that batteries increase voltage and resistors lose voltage. Or as I've said, batteries are like a chairlift, resistors are like a ski hill.